So let's go ahead and take a look at this chart. This is the chart that's on page 25 of your PDF file. And what this does is it shows us the K values, and that's specifically this column right here. It shows us the K values of different acids. Now it has them in order of strength. The stronger the acid, the larger the K value. And the reason why that is because the stronger the acid, the more it will push towards the product side. If you take a look here, if we have some acid, and as this acid becomes products, you can see that the larger the K value, so if the K value is larger, how do we make the K value larger? We make the K value larger by having more numerator. And to have more numerator, that means we need to have more of the products. So the larger the K value, the more products. And again, if it's a larger K value, it's going to be a stronger acid, which means that it's going to become more product. It will dissociate more. Now we're going to use this chart here to help us determine if other reactions are favored, in what direction other reactions are favored. So this is page 24, and what we need to do is we need to underline the reactant that is acting like an acid. Now again, the definition of a Bronsted-Lowry acid is something that loses a hydrogen, that donates a hydrogen as it becomes a product. And if you take a look, this right here is the acid in the forward direction, because as this becomes this, notice how it's losing a hydrogen. In the reverse direction, though, what is acting like an acid in the reverse direction? That's going to be the H3O+, because in the reverse direction, it's becoming H2O. So, in this situation, what we want to know is which of those two acids is the stronger acid. Because the stronger acid is going to drive the reaction in the direction that is away from it. So whichever one is the stronger the stronger acid is going to be the one that's going to dictate the direction in which this reaction will occur. Well, let's go ahead and take a look at this chart. Let's go ahead and find these two acids. If you take a look, acetic acid is right here. And then the H3O+, which is the hydronium ion, is right there. According to this chart, the hydronium ion is the stronger acid. And so what I'm going to do is I'm going to go ahead and write the K value underneath each of the acids on this next slide here. So the K value is 1 for H3O+, and if we look, the K value for acetic acid is 1.76 times 10 to the negative 5. We'll go ahead and write that under there. So when we're looking at this here, the H3O+ is a stronger acid. That means that it is more likely to dissociate. That means it's more likely to push the reaction away from itself. And so what you do is you draw a bigger arrow going away from the stronger of the two acids. Now, in this situation, we're going to draw a smaller arrow going away from the direction of the weaker of the two acids. And if you take a look here, notice what direction is the reaction going to be driven in. It's going to go more towards the reactants, and it's going to not go as much towards the products. And so what ends up happening is, because this here is a stronger acid, it's going to drive the reaction this way, which means that we'll end up with more reactants. And if the K value is products over reactants, and we have more reactants, what type of K value are we going to end up having? Well, we're going to end up having a K value that is less than 1. Now, number 2 is actually an easy one. This right here is a strong acid. If it's a strong acid, is this a reversible reaction? It is not, which is shown to us by this single arrow going forward. Because it's a strong acid, it will 100% go this way, which means that we will have none of this, and we will have only products, which means if we have only products, that means the K value is greater than 1. Now, number 3. I'm going to go ahead and underline the acid. If you take a look, the thing that's donating a hydrogen in the forward reaction is this. The thing that's donating a hydrogen in the reverse reaction is this. Notice how this is an acid, this is a base, but this becomes an acid and this becomes a base. So let's go ahead and look at our K values over here. In this situation, you can see that the water is all the way down here and ammonium ion is over here. So let's go ahead and write those K values under each one on the other page. So if you take a look here, which of these two have a larger K value? And again, a larger K value means there's more products because the acid is a stronger acid. Now, I just want to clarify, even though I say one acid is stronger, they're both weak acids. It's just one of them is not so weak as the other one. So of these two, this one right here is the stronger acid because it's got the larger K value, which means that the reaction is going to be driven this way and it's going to be not so much driven that way. Again, because it's got a larger K value, it's going to drive the reaction towards the reactant side, which means that we will have more reactants, which means that our K value will be less than 1. Now, if you look at the below here, 1, 2, and 3, it's asking us which direction is favored. Well, again, whichever direction has the larger arrow is the direction that's favored. So in number 1, the favored direction is towards the reactants, so the reactants are favored. In problem 2, we're dealing with a strong acid. It 100% goes to the product side. And then in situation 3, we have the reactants being favored again. Go ahead and try these other practice problems, and the key is on my website.